Okay, I wanted to give you guys a better diagram of an electromagnetic wave, although now that I'm filming it, I don't know that it came out much better. Okay, but now I really want to start talking about wave behaviors at a boundary. So, wave behaviors at a boundary. So, oops, I don't know if you can see that. So wave behaviors at a boundary. So let's say we have a wave that starts out in a dense medium, and I'm just going to send one pulse through that medium. And then it's going to transmit into a less dense medium. Now I'm representing this by slinkies because that's how I would have done the demo in class. So now I just want to draw out what that pulse would look like in the slinky. So let's say it's something like this. So we have a dense medium, and that wave is being transferred to a light medium. Well, one of the rules is that once a wave is created, the frequency remains the same. So once a wave is generated, the frequency will remain the same. Well, if the frequency is going to remain the same, and if I tell you that in a dense medium the wave moves slower, and in the light medium the wave moves faster, then just based on the formula I gave you, V equals F lambda, if the speed has increased in the light medium and frequency remains constant, right? This won't change. This is constant. Then what's going to happen to the wavelength in the light medium? Well, it must increase also, which I showed in this diagram. So here we have a small lambda, small wavelength. Here we have a large lambda. Now, one of the other things I want to point out is that when it passes this boundary, because it's going from dense to light, this is going to be, will be sensed as a loose end. So the wave will go through on the same side. Okay, so wave passes through on the same side of the medium. However, if we have a wall on either side of this setup, so let's put a wall here, wall, and a wall here. That wall is a fixed end, so the wall will act as a fixed end, which means that once the wave transmits into the lighter medium, if it reaches the wall, it's going to invert itself, because it's experiencing this as a fixed end. Thus, when the wave is reflected off the wall, it will invert itself. It will invert itself. And of course, at that point, in other words, the wave is being reflected. Wave is reflected at the boundary. Okay. And once it's reflected, obviously it will have lost some energy at that boundary, meaning the amplitude of the wave, which we said is reflective of how much energy it has, will be smaller. Okay, so some of that energy will be lost at the boundary. Really, it'll just be converted into heat energy. Because we know that energy isn't truly lost. Thus, the amplitude of the reflected wave will be smaller. The amplitude of reflected wave will be smaller. So there are three things that happen at a boundary. Three things that happen when a wave reaches a boundary. 1. Some of the wave is transmitted. Some of the wave is transmitted. Number 2, some of the wave is reflected. Some of the wave is reflected. And number 3, some of the wave is absorbed. Okay. Now I do also want to talk about what happens at a different kind of boundary. I want to talk about something called diffraction. So diffraction is actually when waves spread out or bend around a boundary. In other words, in our little classroom, we have the wall, and if I leave that door open, all of the sound that is coming from me, the source, all of the sound coming from me will reach this boundary. Some of it will get reflected back at me. Some of it will get absorbed and lost, transferred into heat. But some of it will pass through out that door into the hallway and actually do something called diffract, meaning it will spread out and people will hear me speaking. Okay, so the degree to which the wave is going to bend around a boundary actually is determined by the size of the slit here. Okay, so size of the opening determines the degree of diffraction. So if you have a really big boundary, or a really big slit, I should say, if this was wider, you wouldn't get as much bending happening. Okay, so if I had a slit that was like this, and here's me, the source, sound is propagating towards this boundary, you're not going to get a whole lot of spreading happening. It's going to be really, really minimal. So the smaller that opening is, right, so large slit equals very little diffraction, very little bending of the wave. I'm not sure if you can see this. Bends minimally. Okay, whereas if you have a really small slit, there's going to be a lot of bending of that wave, and that's called diffraction. So I'm going to link you guys to a PhET simulation. PhET simulation on diffraction, so you can kind of mess around with the size of the slit and see what kind of effect it has. I want to look really quickly at double slit diffraction with you. So double slit diffraction would be if you had 2 slits rather than 1, double slit diffraction, because this is actually going to cause wave interference. So let's say you had a little boundary here and here. And let's say you have one source on this side that's generating these concentric circles that are representing wave fronts. And now these wave fronts encounter a boundary, and what's going to happen here is you're going to get waves spreading out around this boundary, like such, as well as waves spreading out around this boundary. And so what you'll get is interference anywhere these waves overlap with each other. Okay, so at all of these points right here, so I'll just mark them off, you're getting wave interference. Okay, so if you have 2 slits, you're going to get these wave interference patterns happening. Okay, so 2 slits will result in wave interference. And there are 2 types of wave interference. There is constructive and destructive interference. Constructive and destructive interference. Constructive interference is when 2 waves meet in phase with each other. 2 waves meet in phase, meaning the amplitude will be additive. Amplitudes are additive. When destructive interference happens, 2 waves meet out of phase with each other, meaning they cancel each other out. Cancel each other out. So I'll do more about wave superposition and wave interference in the next video.